today we're going to talk a little bit about a new topic, or maybe a lot about the new topic, LQMs, large quantitative models. It's just beyond the text generation. These large language models would mostly train on language, and these new models are something kind of exciting one. And I'm going to ask our guests to talk about it, but just generally, I wanted to make you familiar with what we are going to talk about. Our guest is a superstar physicist turned AI researcher. So Stefan Leichenauer is currently the VP of engineering at SandboxAQ. He focuses on advancing capabilities of models. With PhD in physics from Berkeley, Stefan brings deep scientific rigor to this world of artificial intelligence. He's passionate about developing scalable AI systems. His work contributes to building more steerable quantitative AI models. Great to have you, Stefan.
Thanks, Steve. Great to be here.
Awesome. Yeah, I mean, super successful and interesting background in the world of science, graduating from top tier universities, working on some of these great projects, from being a researcher at Alphabet to now driving the AI innovations in a very interesting, innovative project, SandboxAQ.
Yes, no, I consider myself very lucky to be not only alive at a very interesting time in history, but being able to participate in a lot of very interesting things happening right now, whether it's on the physics side in my previous career, and now on the AI side. So many interesting things, so many interesting breakthroughs, so many interesting opportunities for impact, and it's all happening right now, which is very cool.
Perfect. I mean, I'm going to just jump right into it, right? Okay, so what are the type of problems you're trying to solve with AI?
Yeah, so as you were saying during your introduction, a lot of what AI is being used for right now is on these language-based problems, right? Large language models, very natural tool for language-based problems, right? They're trained on the internet. They can analyze they've analyzed a lot of text, and they can do a lot of interesting things, content generation and so forth, multimodal content generation, even moving beyond strictly like text. And that's great, but it leaves on the table other problems which are not text-based, not naturally language-based problems, right? Which a language model alone is not the best tool, right? And these are the so-called quantitative problems where quantitative AI comes in. So just to name a few examples, the kinds of things that we work on at SandboxAQ. One example, big category of examples, is on next generation drugs and materials, right? Drug design, materials design. These are physical things that you have to make and then use, and they're supposed to solve problems. They have new materials with new properties, right? This is not a language problem. This is a physical world problem. Other kinds of problems include, next generation medical devices, right? New medical diagnostic devices. What is the next MRI machine, right? The next generation version of an MRI machine that's going to be very useful from a healthcare point of view. This is not a language problem. What about, there's a problem right now with navigation, right? We rely on GPS for navigation, but GPS is very vulnerable. It can go down. It's not super reliable all the time. How do you figure out where you are and where you're going in novel ways? That's maybe something we can touch on in a bit. And all kinds of problems related to cybersecurity. We touch on all of these kinds of things at SandboxAQ and more, but these are just very clearly not language problems, right? And there are a lot of people out there, organizations, customers of ours who, need to solve these problems. And in order to, move forward, we as, humanity need to make progress on these kinds of problems. So that's really what we're after, and that's what we're about.
Awesome. I mean, you touched on great use cases. Like these are all very important ones. As you mentioned, like not all problems are language problems. I mean, large language models, we all already know about some of the use cases. I mean, most of the use cases are out there. We're generating lots of great text. Students getting great marks, and that's awesome as well. But what happening here is, this is not the only solution for all the problems. It's not the sort of silver bullet. And I would like you to, expand a little bit on the other model that we mentioned briefly. Like, what are the differences between LLMs and LQMs, and in terms of capabilities, applications, and which one you're using for your project?
Yeah, no, it's a great question. So this large quantitative model, LQM, this is a term that refers to the kind of model or the kind of system which is engineered to solve these various problems I was talking about, and others. The first thing I think to know about LQMs is that it's not just a single thing, right? So if we take a step back and look at LLMs, right, large language models, what are those, right? So there's a few, there are different flavors of LLM, but they're all mostly the same kind of thing. It's a single monolithic black box style model built out of the transformer architecture from actually many years ago now, back in 2017, the transformer architecture was introduced. And it's the last several years have been about taking that same basic ingredient, making it bigger and bigger, ingesting more and more data, and getting some powerful model out of it. And that's a kind of a simple picture of maybe an oversimplified picture of what an LLM is, but okay. An LQM is a bit different. So the way I think about LQMs, first of all, if I had to give just like a one-liner, which is insufficient, I would say, all right, certainly machine learning is involved, and the way that the kind of data that we're talking about and the kind of applications, or the applications I was talking about before, data having to do with these more quantitative problems, not just text. But to say a little bit more about it, the idea of an LQM is not as a single big monolithic model that's going to solve all the problems, right? I prefer to think about it, or it's better to think about it as a system with modules, like a modular system with different components. And those different components can do different things, and you can get different LQMs by wiring together those different components in order to solve whatever problem you're interested in. Some of those components should be machine learning type models, neural networks, and so on, of varying architectures. We can use transformers if we want, but we don't have to use transformers. But I think critically, other parts of an LQM are not even necessarily doing machine learning. Like, we have other computational tools available to us, other kinds of advanced computation that we want to be able to take advantage of. Things that would ordinarily be in the category of like high performance computing, for example, or like traditional scientific computing. These are our abilities to like solve equations, right? And there are all kinds of different ways to solve equations, fundamental equations that must always be true. We can solve them numerically. We can solve them in lowbrow ways, brute force ways. We can solve them in more sophisticated ways. We can try and use machine learning to solve them. And there are lots of different techniques. And an LQM is kind of about piecing these things together and creating workflows that allow you to, say, generate new data by solving equations in a situation where the equations apply, but you haven't been before, and then taking that new generated data and training a machine learning module of the LQM to do to do something interesting, to say scale up your ability to understand this system in a new way. So it's a little more complex than just a single model, but it also is necessarily flexible because we're trying to look at all different sorts of problems. I mean, the same LQM is not going to generate a new material as it's not going to both generate a new material and solve problems in global navigation. You wouldn't use the same model for both, if that makes sense.
Yeah, that's great. I mean, very helpful, because a lot of us have heard about LLMs, and this is a very good way to differentiate them. As we can see, also LLMs are becoming smarter in a way that they're using mixture of experts. It seems that like these new models, like these open source ones that we can see what's inside, are doing it. So it seems that that's one of the better ways to leverage these big models rather than a huge monolithic model. We would have more of like experts to help each other. And these large quantity models actually taking it further by adding a lot of extra layers and helping things that are not necessarily being solved by the language. I mean, I remember even the smartest models had problems with calculations. I mean, very, very rudimentary ones, not even the super smart, like something that you would do it. A 10-year-old could have done it, would be a problem. Or even like counting R's in a strawberry was kind of a meme. I think at some point somebody hard coded it to the LLM to just get rid of it.
I wouldn't be surprised. Yeah, I think you're absolutely right. And I mean, I think that those examples kind of they automatically illustrate like a few different issues, a few different reasons right away, if you dig in a little bit, as to why an LLM should not be the only tool in the toolbox for working on these kind of very critical issues that we want to be working on. So the issue of the calculation is an interesting one. So yeah, LLMs are getting better at calculating, and these days you might give the LLM a calculator and let it make calls to the calculator, and so even LLMs are drifting more into this LQM direction. But the other interesting thing about these examples is that when the LLM makes a mistake in these areas, it doesn't tell you that it's made a mistake, right? It's always very confident that it gets the answer right. It's very confident that there are 2 R's in strawberry, right? Or whatever the problem is. And when it's when you're doing something, when the answer matters, right? When you're not just creating marketing copy or something, or generating images of cats and dogs, when you're doing something where lives or billions of dollars may be at stake, you want to know that the answer is right. And this is one reason why having these different handles on the problem through these different sort of modules, like when I talked about generating new data by solving equations and so on, these are things that we know are true and we can check. And maybe the machine learning component of our system gives us an answer. Well, the first thing we would do with that answer is we would try to check it as much as we can, right? Make sure that it makes sense, make sure that it is valid according to fundamental laws. We want to reduce the level of mistakes, and LLMs are always going to be LLMs alone would always be subject to hallucinations.
Yeah, that's very important to mention that at some point we are going to still get mistakes and hallucinations from LLMs. I mean, they are meant to have this problem because of inherently the design and the algorithm itself. Yes. But also you mentioned LQMs and improve over time. So can you tell us how does exactly happen and what does it mean that the future of AI-driven insights?
Yes. So maybe I can illustrate this point and all of these points using kind of an example, right? So there's an
Sure.
example I like. It's not a business case example, but I think it's a useful example, and that is the example of predicting the weather, right? Let's say you were interested in predicting the weather. So the weather is clearly not a language thing, right? It's a physical system, and we understand the basic principles behind the physical system. And you could ask an LLM to predict the weather if you wanted, and if it's read a lot of weather reports, which it has, it's probably done a pretty good job. It'll probably do a pretty good job, right? Maybe a surprisingly good job, because LLMs are surprisingly good at a lot of stuff. But the reason is because it's read a lot of weather reports. It's kind of like a fancy almanac in that way. It's like using the past to say something about what's going to happen next. But when there's a hurricane coming your way, and you want to know where it's going to hit because, well, it's going to cause a lot of destruction, you need to do a little bit better than that, a lot better than that. You need to be sure of what you're doing. And so the LQM approach to solving this problem is not to just read a lot of weather reports, but it's to have a model which has ingested a lot of actual weather data, right, from sensors all over the world, and has learned and knows something about what the weather actually is in order to make a prediction. But more than that, what the LQM would do is leverage not just the machine learning and the weather data that we have from our sensors, but the supercomputers that have been for decades now computing weather, filling in the gaps in our global weather data by using, computing, because we know that the atmosphere is a fluid and we can compute what's going to happen. And there's a lot of generated data that has been made by supercomputers over time, and will continue to be made by supercomputers over time to get more and more fine-grained, reliable weather data. The problem is that supercomputers are expensive and relatively slow, right? So what you can do with all that supercomputing data is you can take it all of that you've computed, use it to train a new machine learning model, use it to train a neural network, and then that neural network can generate predictions for you very quickly, much more quickly than a fresh supercomputing calculation. And that's the thing you would actually use to say, okay, where's the hurricane going to go? But if you want that neural network to get better, if you want to improve your weather prediction, 10 years from now, we want the weather prediction model to be even better. How do we do that? Well, the way to do that is to generate even more data using the supercomputer, improve the supercomputing side, generate more and more reliable, trustworthy data, in addition to taking data with sensors. And then you can train an even better weather prediction neural network. And so it gets better over time in the same way that any other neural network would get better, just by having more data. The difference is we have ways of generating the data, right? Using things like equation solvers. And rather than just waiting around for a supercomputer to generate data for you, what you can do is you can wrap the sort of supercomputer side, or something analogous to the supercomputing side, together with the machine learning side, put those things next to each other, and then put a box around it. And now that thing could be a self-contained LQM that can go on autonomously go on a virtuous cycle feedback loop to improve itself over time, or given a new situation. Or we could take the same, and if I continue with this weather example, we could imagine taking this same structure of these two halves that work together and use it to fresh from scratch predict the weather on a different planet. And it's going through this process of generating data according to what's going on that planet, and then learning from that data, and then going forward like that. So that's rough structure of how an LQM could work in this situation.
That's super impressive. And yeah, you mentioned some of the great points about one example. It's a real use case, and we already know that LLM cannot help with this. I mean, it would have been fun if we wanted to predict the weather using the language model. But anyway, there are lots of use cases like that cannot be solved using an LLM. Can you give us more of examples of real world use cases of LQMs that are helping some in solving interesting challenges that LLMs can't do?
Yes. So let me give an example. Let me give an example that we're working on at Sandbox. Something that I mentioned earlier. This problem of navigation, right? So to say a little bit more about the problem, if you're trying to fly a plane somewhere, you're relying on GPS to tell you where you're going, but GPS can be spoofed. It can be blocked. The satellite could fail in some way. Basically, you're relying on this external thing, this satellite signal, to tell you where you are. And in the event that there's something interfering with that, you're in trouble. And I mean, before we got into this area at Sandbox, I was not aware of how much of a problem that really was. But actually, if you read the news, these kinds of things happen all the time, especially in areas around the world that have lots of conflicts in them. So what do you do in that situation? In that situation, you want to be able to navigate around without relying on some external body telling you where you're going. What can you do within yourself? And there are many things you can do. There's a whole lot of options, but one that's very exciting that we particularly like at Sandbox that we're working on, that we've demonstrated in practice with the U.S. Air Force recently, is magnetic navigation. So in this example, you're going to fly around, and it's similar to how birds navigate long distances. What they do and what you do is you try to pick up the tiny changes in the magnetic field due to different rocks, say, that are in the Earth's crust, and you have a map that you've got downloaded onto your system. You fly around, you pay attention to what's happening to the magnetic field, and basically can tell where you are, because the magnetic field, the tiny changes in the magnetic field, are like a fingerprint on the Earth, so you can tell where you're going. All right, so that's the problem, and that's the proposed solution. But what makes it hard? Part of it is these magnetic signals you're trying to detect are very small, and there's a lot of noise, right? There's a lot of electronics on the airplane making a lot of magnetic noise. There's all kinds of the metals around. It's a really challenging signal to noise kind of issue. And this is a problem that you need to solve at the software level. And the way that you solve it is, the way that we solve it is in this LQM style, right? And so what does that mean? Well, it means that at the end of the day, there's some machine learning that's happened, right? There's some machine learning that's told us, all right, processing the signal, because you need to do it very fast. And so you process the signal, very quickly process it, and output some cleaned signal that says, here's the local magnetic field and here's how it relates to this map. But the way that model was trained, the way that you improve that model over time, is by using a lot of physics-based data. So the magnetic field is a physics thing. You can have a physics model of the airplane that you're flying in. You know the physical origin of a lot of the noise sources, like the electronics in the airplane. And if you want this model to be able to work, or to be able to adapt to different airplanes with different kinds of cargo on them, flying in different regions, you need to be able to know how those physical changes will affect the problem that you're interested in, or what the effect is on the ultimate model that you're talking about. And so again, it's this interplay between, let's generate some data, let's use some physics-based insights, some things that we understand in order to generate a lot of data, train an ML model with that in mind, and then use the ML model kind of at inference time. We're not doing any slow equation solving. We're just using the sort of ML side of it in order to be able to execute quickly and rapidly. And so that's another example of one of these quantitative problems that has its roots in some physical process that we can understand and get data out of, and proceed in that way.
Yeah, that was a great example, and it just brings it to life, because a lot of times, like, you would have concepts and interesting from a technology perspective, but like, who is using it and how it can affect us. And I know that, like, LQMs are already helping in other domains, like biopharma, material
Yes.
science, energy, and lots of other places that AI is helpful, but not necessarily the language models are going to do the job.
No, exactly. And the biopharma is like a big one, obviously. If ultimately we're interested in having drugs that cure diseases, right? But that's a very complex problem. It has its roots in, again, a physical process, and we can talk about the binding of molecules, and what the LQM approach to this problem would be, okay, let's look at the physics of that and how that works, and generate data by solving equations, and then train ML to shortcut but then there's a whole other side of that problem, which goes beyond the physics and into the biology. By the time you get to clinical trial, 90% of drugs will fail. How do you improve that? A lot of it has to do with very complex pathways in the body. How do you know if something is toxic or not? When if I were to ingest a new pill, is it going to harm me? There's a lot of complications there. It makes it hard to it would be very challenging to try and model all of that all the way down to first principles equations, right? And so there are actually other kinds of LQM tools that we could bring to bear in situations where where fundamental equations don't tell the whole story. You can use other things like these tools called knowledge graphs, right, which encode relationships between concepts, right? And you can make it causal, like, okay, this causes this and this causes that, and you have a whole map of ideas or concepts, entities, and causal relationships between them, and maybe millions of these concepts and relations between them. And you want to build that up over time based on experiments, based on generating new data to fill in little pieces, and then having that kind of knowledge graph that encodes causal relationships between very complex things is another tool that you can have, that you can rely on and test over time, and it's very interpretable and transparent what it's telling you, and you can use advanced computation to extract insights out of that too. And so it's like another tool in the LQM toolbox. You've got the equations for when the system is for very reliable data generation. You can encode more complicated situations into these like causal knowledge graphs. And then you've got neural networks and machine learning that can take all of this data and supercharge it. And putting these ingredients together to solve hard problems is the name of the game.
That's great. I mean, this is very helpful, and as I said, like, it's already showing the potential and the impact. One of the criticisms of LLMs is just like enterprises are struggling to actually leverage them at scale in production. Most of them either staying at the POC or MVP sort of stage. How these LQMs are overcoming this problem and delivering real value to the business?
Yeah, no, that's a great question, and it's true that LLMs should be useful for a lot of stuff and are being integrated all over the place. One very exciting area is LLMs for coding. Engineers using LLMs to allow themselves to code better, which should lead to a lot of efficiency improvements. But that's just the thing, is that a lot of the LLM use cases, the pure LLM use cases in a business context, are all geared toward efficiency and cost cutting. And can we do what we're doing already, but faster and cheaper? And there's a calculation you have to do there. You need the thing to be reliable enough, cheap enough, fast enough in order to reduce your costs. But that also puts a cap on the total value you can get, right? Or a strong, maybe not, anyway, it's limiting in a lot of ways, right? If it's fundamentally about cost cutting, it ends up being limiting. And that means the standard for, do I adopt this or not, becomes quite high, right? Because you're already solving those problems in other ways, and you're just trying to find efficiency. In the LQM case, the problems we're trying to solve are really about value creation, right? Doing new things, going into areas. One theme of LQMs, which we've touched on a few times, but I'll say it much more explicitly now, it's about data generation in areas that we haven't yet explored, right? So if we had already figured it out, if we'd already figured out, say, how to make the right drug to cure Parkinson's disease, if the information that told us how to do that was in the internet and existing in the scientific literature already in a simple way, the LLMs would have found it for us, right? Because that's what they're good at. They're good at ingesting a lot of data of what's previously known. But LQMs are about going beyond that, right? And going beyond that reliably. And that's why a lot of the first step in an LQM system is generating new data in a domain that goes beyond where our existing data is, and doing that reliably, right? Grounding that in fundamental truths, equations, knowledge that we're very confident in, and in a way that is testable. Because that's how you make progress in new directions. That's how you can create new value. And so the business calculus is totally different. To use another quick example, like a hypothetical example, if you're like a car maker, right? If you're making cars, if you're an automaker, you could use an LLM, and you probably are using an LLM to help you write marketing copy for your car, come up with new designs for what's going to be appealing for the consumer, that kind of thing. But if you want a better battery for your car, right, that's going to help it. It's going to reduce the weight and be able to go further for an electric vehicle. If you want a new material that the car is going to be actually made of, that's going to be strong and light and cheap. If you want to do a lot of virtual testing of your car, you want to do virtual crash testing or something like that. All of those kinds of problems aren't going to be solved by LLMs, and those are very high value problems. And so using LQMs just naturally are built to attack high value problems, which makes them more attractive from a business point of view and an adoption point of view.
It's so fascinating. I mean, I can kind of understand it from other point of view. If you think about the brain, you have different parts of brain responsible for different things,
right,
and they
right.
all have different perception of things, and they work together closely, making the final outcome. We don't know exactly how the brain works, but we would already know that. So there are part of brain responsible for visual process. There are parts of brain responsible for maybe emotions and things like that. So I can see like there are certain similarities in terms of how LQMs are kind of encapsulating different functionalities and working together to deliver the final result. That's super exciting. For the final question, I know that like we can talk about this for hours, and I would love it, and I'm sure that our audience is going to love it. But we're kind of getting close to the end of this session. We'll definitely come back to you, Stefan, for another podcast. But for the final question, I would love to know a little bit about the future.
Yes.
That's an exciting one. But like, if you fast forward to 5 years, how do you see these LLMs are evolving and helping businesses to change and impact our lives?
Yeah. So I think we're at, we opened the discussion here talking about how we're at a very interesting time in history where a lot of these problems are now being solved, and there's a lot of excitement happening in AI and in AI combined with other fields and so on. And so I think we know that 5 years is actually a very long time, right? Very long time where we are now. So I expect a lot in the next 5 years. In the next 5 years, a lot of the problems that we're starting to solve today, like, okay, we're starting to see ways that we can improve and accelerate our drug discovery and materials design. We're starting to see ways that we can have GPS-free navigation. We're starting to see new ways of making medical devices and things like that. So by 5 years from now, a lot of those things that we've started today will have been done. We will have drugs and materials and so on that have been AI designed. And that at that point, we should be setting ourselves higher. At that point, we should be making dents into some of the really grand challenges that those build into. I'm talking about things like energy and climate, right? So, for example, green chemistry is a big theme that I would love to see progress on in the next 5 years. So everything that all the materials we have, all the consumer goods that we have, we should be reformulating all of that in new ways, using new materials, using new chemistries in order to be sustainable and environmentally friendly and not so reliant on fossil fuels and petro-based products. All of that, there's really potential. 5 years from now, we should be making dents in those kinds of problems. And a lot of hopefully by then also, or around that time, we'll start to see real progress on actually curing some of these diseases, the big diseases. We're talking things like cancer. There could be like many cancers could be essentially taken care of by drugs that are designed in order to combat that cancer. And it should be very exciting. Perhaps I'm an optimist, but I think it's the fact that you can make those kinds of statements on a 5-year timeline and not be, if you had 5 years ago, if you had said 10 years from now, right, we'll be doing this, you would have sounded much more crazy than saying those things today about 5 years from now, right? And that's, I think, very encouraging.
That's awesome. I mean, I love the excitement, and I share the same optimism and excitement about how things are going to evolve and how AI and LQMs in particular are going to evolve and change the way things are done right now. I mean, we had these dog year, which was much faster, and now we are in the GenAI era, which is another word. When we are talking about like what's going to happen in the next year, sometimes people it's like next year. It's very long time.
That's so long from now, right?
It's so long.
Things
going to change drastically.
Yeah. By this time next year, the AI agents will be doing all of this stuff for us, and we'll all be doing something else.
Exactly. Yeah, I'm excited to go to the beach and drink some orange juice and enjoy my life. If AI agents disrupt my role, so that's something that I'm looking forward to it. But thanks, Dr. Stefan Leichenauer. It was great to have you. Any final thoughts?
Well, I think this was a really great conversation. Once again, I'll say I'm very optimistic about the future. I think the this path that we've started down collectively is a very interesting one. We're going to see more and more of these grand challenges ahead of us start to fall, using LQMs, using LLMs, using all of these ideas together. Let's use all the tools we have in our toolbox, right? More is better. And it's going to be very cool. And next time we chat, I'm sure we can talk about all the problems that have then been solved.
100%. Yes, we'll have you back to look at what have changed since our discussion. Thank you very much. Thanks, everyone.